Hello, this is Sharir Papan, and in this video I'll be going over the Capstone project for the Class EE 120 Summer 2026 C semester. Um, so the initial task was to basically interview stakeholders, friends, or TAs, teachers, and kind of get like the features and requirements down. And some of the from reading the facts, some of the requirements were already given, like um, we have to have like a limited number of failed attempts, and I chose three because that, according to some of my friends that I have interviewed, that's like one of the most common and um, expected lockout limit. Like on your phone, for example, you'd get three attempts. Um, and then the main thing that kind of started off the designs is basically the state definitions. And here I have my state table given, and I also have like this encoding table, even though I don't think it asks me to make the encoding column, but it really did help to just have it here so I didn't have to restate it when I'm making the state diagram. Um, yeah, so basically four states, five states, starting from S0 and ending at S4. Starting at armed or wait, and then you have your incorrect password attempt 1, 2, and 3. And instead of calling it like incorrect password attempt 3, we can also call it lockout, or like when reset is required. Um, and we did have to go with like three bit width, so we have like three binary digits here because there are five states, so we were gonna need at least three binary bits to actually represent all of them. But that also means 2 to the third is 8, so we have 8 possible states for three, or 8 possible combinations for three of these, and we only have 5 states, so 3 of the combinations are going to be redundant or kind of unused. Even though we didn't do this design, because later I evaluated design 2 to be better. Here's the state diagram. It's pretty simple. It just shows all the transitions basically, and then I also have the transition table here. I kind of combined the state name and the encoding together here instead of having like 2 extra columns. And we have our P and F. Obviously, P represents if P is 0, the user is typing something. If P is 1, or P is 0, user is not typing anything, the input is empty. And if P is 1, the user is typing something. In accordance with F indicates the correctness of the input. So if F is 1, the input was correct. If F is 0, the input was not correct. And then we have our maps, our kind of designs here, and the equations, pretty simple. And then the equations are pretty kind of simple to derive once I have decided like how the flip-flops were gonna like work and how many flip-flops I need. And let's see. And then next, we went to design 2, and for design 2 I actually decided that we don't really need like a open state, because the open could just be the instantaneous response once the, like on the same clock cycle, once the password is correct. So I actually decided to go with four states instead of 5, and that also means that we can use two bit width of 2 to represent our encoding, because there's only 4 states and we can use 2 bits to perfectly represent 4 states. So I have wait attempt 1, so this would be like the failed attempt 1, and then failed attempt 2, and then failed attempt 2 can either just after failed attempt you have like lockout, and lockout will be dependent on whether your the kind of instantaneous attempt was correct or not. So it's either going to go to lockout or just open and then lockout. Because I've decided that even after you open it, if there's an open state, it's gonna automatically go to lock again, because if you close like the gate, it should be armed instead of like waiting for the gate to be closed, because that introduces like more extra like way too many things that I'd have to consider, like edge cases. If I'm trying to make it like manual, like you have to detect when the gate is closed and then arm it. So instead, you just arm it right after it's opened. So after you close it, it's not um, it's not open by default. And here's the state diagram, evidently much simpler than the first one, and the transition table is also much simpler than the first one. Equations are also pretty simple here. And then I have the weight system, or weighting, or weighing, not weighting. And I chose like ease of implementation, and that kind of incorporates logic gate count, flip flop count, because I would say the more logic gates you have, the less easier it is to implement. And then clarity, or like I kind of call it like state behavior intuitiveness. Like if you're reading the circuit, how intuitively can you understand it? How clear is it? And then efficiency and speed. So I weighed them 20% for ease of implementation, 30 for gate count, 20% for flip flop count, clarity 15%, and efficiency or speed 15%. Efficiency and clarity was suggested by the people I interviewed, so that's why I added them. And then the way I applied my criteria is pretty simple. So you have design 1 score and then design 2 score. I scored all of them from 0 to 10 for each of the criteria first. And then obviously I multiplied each of the corresponding score with the corresponding weight in decimal form here, corresponding weight, and then summed them. So you have the weighted total. And here we can see that the weighted sum shows design 2 wins pretty strongly actually. So I choose design 2, and then I started kind of like designing it in digital, kind of like messing around with it to see like what inputs I need. And here I have like kind of like the explanation of why I chose the criterias. And here's the final kind of design. Obviously I didn't add like the clock component. It's kind of like the labs we did in class. I just have a CLK input that I can click and like incrementally go up. And the combinations would basically be like Y, the output, and the Q1 and Q0 for the basically unique combination of outputs and what do you call it, pairing, right? And here I have kind of tested some of these, and for some reason the last state did not actually meet the expected state. It just went straight to 0 0 0 instead of like having I'm not sure why this happened. Maybe I reset it somehow or mapping, but I deleted some of the wiring and reconnected it, and then it worked. So that, I'm not sure why that worked. And this is the video I'm recording now, and yeah, that's basically it. And I can actually show it in digital here. Here is the circuit, and if we keep clicking CLK, we can see it will increment, or not increment, kind of like show different combinations. I can reset and then just go back. Yeah, you can see password is on compared to password is off. Reset. Yeah, so yeah, that's basically it. And yeah, thank you for watching.